Setting up your AI workstation is a critical first step towards enabling powerful machine learning workflows, deep learning experimentation, or scalable inference tasks. Whether you're deploying models, training neural networks, or running intensive data analytics processes, your hardware and configuration choices lay the foundation for optimal performance. Let's walk through detailed step-by-step instructions for getting your AI workstation operational, tuned for speed, and reliable under demanding workloads. Begin with unboxing and assembling your hardware. Ensure all components are compatible and seated securely. Your CPU, RAM, GPUs, motherboard, and storage devices should all match the specifications required for AI workloads. For deep learning, high-memory GPUs like NVIDIA's RTX or A-series cards offer considerable advantages. For CPUs, multi-core architectures facilitate efficient data loading and parallel computation. Fast NVMe SSDs dramatically reduce data transfer bottlenecks during training and large-scale data pre-processing. Double-check the PSU wattage to guarantee stable power delivery, especially for multiple or high TDP GPUs. With hardware assembled, the next step is installing your operating system. For most AI applications, a Linux-based environment is recommended due to superior support for machine learning libraries, drivers, and scripting automation. Ubuntu LTS releases, such as 20.4 or newer, are preferred for stability and compatibility. Insert your USB installation media and boot into the installer. Select your language and region, configure the keyboard layout, and proceed to disk partitioning. For AI workstations, it's advisable to divide your storage. Allocate sufficient space for the root partition, at least 100 GB. Create a separate home partition for user files, and dedicate a substantial section of your fastest SSD or NVMe drive for data or MNT data to house large data sets and checkpoints. During installation, enable the option to download third-party drivers and software updates. This ensures network and GPU drivers are installed from the outset. Set up your user account with a strong password. When installation is complete, eject the media and reboot. Upon first login, update your package lists and upgrade the system by running the standard commands in the terminal. Sudo apt update, followed by sudo apt upgrade. This step resolves security vulnerabilities and ensures your base system is current. Next, install and configure your GPU drivers. AI workflows are heavily reliant on GPU acceleration. Correct configuration is essential for frameworks like TensorFlow and PyTorch. For NVIDIA cards, use the Ubuntu drivers devices command to detect recommended drivers. Then run sudo ubuntu drivers auto-install to install them. Once installed, reboot. Verify the installation with NVIDIA SMI. This utility should display your GPU's, driver version, and basic statistics. For advanced GPU management, consider also installing NVIDIA CUDA Toolkit. Download the appropriate version from NVIDIA's developer portal, matching your GPU architecture and the libraries you plan to use. Follow the toolkit's instructions, adding export lines to your bash, to update your path and L library path. For deep learning, you'll commonly require QDNN, a set of GPU-accelerated primitives for deep neural networks. Register and download the appropriate QDNN version from NVIDIA, then extract the files and copy them to your CUDA directories. Typically, USR, local, /CUDA sys. Update permissions as necessary and confirm successful installation by checking the library files under /USR, local/QDA lib64, and include directories. Other dependencies for end-to-end AI workflows include Build Essential for compiling software, GIT for version control, Python, preferably via Anaconda or Miniconda for easy environment management, and libraries like OpenCV, HDF5, and various Python or R machine learning tools. For code editing and debugging, install a robust IDE like Visual Studio Code or PyCharm. Python environments are essential for reproducibility and library management. Anaconda or Miniconda allow isolated virtual environments, minimizing package conflicts. Download the installer from the official source, run the bash script, and follow the prompts. Update Conda. Ask Conda update Conda, and create a new environment for your AI tasks. Conda create cha yanan I env Python 3.10. Activate it with Conda Yees activate AI env. Install machine learning libraries. For deep learning, run pip install TensorFlow and or pip install Torch Vision Torch Audio as needed. Verify that each framework can detect your GPU by launching Python and running the appropriate commands. tf a config.list physical devices GPU for TensorFlow or torch.studio as available for PyTorch. Fine-tuning your RAM and storage settings is key to sustained high performance. Enter your system's BIOS or UEFI menu by tapping the designated key during boot, often F2, Del, or EOS. Verify that your memory is running in the optimal profile. Look for XMP or DOCP profiles and enable the highest stable frequency listed for your RAM modules. This can yield significant improvements in data throughput during large-scale mini-batch training. Ensure memory is installed in the correct banks to enable dual or quad-channel operation, maximizing bandwidth. For storage, leverage the fastest drive for datasets and active projects. Keep your OS on a separate partition or device to minimize contention. If using Linux, configure fstab entries to mount your data drives with options that optimize performance, such as NOAA time. Monitor drive health with tools like Smart Settle and reserve space for swap, especially if your RAM is under 64 GB. Software-level optimizations include adjusting your system's swappiness parameter, e.g., sudo sysvm.swappiness, SHA-10, to reduce reliance on swap space in favor of RAM, speeding up AI workloads that can saturate memory. Enable trim for SSD longevity using the fstrim utility or by activating periodic trim in systemd timers. For systems with multiple GPUs, install NVIDIA's NVIDIA Settings tool and use it to manually assign workloads to specific cards, or configure explicit GPU visibility per process by exporting CUDA visible devices in your scripts. For maximum stability and performance, consider employing system service units to launch commonly used AI servers. Use lightweight display managers and desktop environments to conserve system resources, or for headless servers, run only a terminal or remote desktop service. Benchmarking your workstation quantifies your tuning and ensures your setup is delivering its theoretical maximum. Start by running synthetic GPU benchmarks. Tools like NVIDIA's CUDA sample codes, bandwidth test, device query, include metrics for PCIe transfer rates and GPU compute capability. For practical deep learning performance, download standard training benchmarks. The MLE inference and training benchmarks offer widely recognized test suites, while frameworks often include built-in benchmarking scripts. For example, train a ResNet50 or BERT model on sample data and log metrics such as images per second or token throughput. For storage, tools like FIO, AgeParm, HBO, or DD can measure your read-write bandwidth and I/O latency under various queue depths and file sizes. Monitor system-wide resource utilization using HTOP, NVIDIA SMI, and IOStat. During benchmarking, ensure that CPU load and process affinity correspond to expectations. CPU bottlenecks, underutilized GPUs, or slow disk access are often visible in real-time stats. For RAM, tools like FreeOH or ATOP allow you to watch how memory and swap are consumed under stress. If benchmarks fall short of published or expected values, systematic troubleshooting can resolve many common issues. Start with driver and library version mismatches, a frequent culprit. Ensure your CUDA, QDNN, and deep learning framework versions are explicitly compatible. Use NVCC version and cat USR local/QD version.txt to verify your installed QDA release. Within Python, run import torch Print a.torch.version.suda to check torch and CUDA alignment. Thermal throttling often degrades performance under sustained load. Monitor your CPU and GPU temperatures with LM/sensors, NVIDIA SMI, or manufacturer tools. Clean your system's fans and heat sinks, and consider replacing thermal paste or installing improved cooling solutions if thermal readings are consistently high. Unexpected application crashes, kernel panics, or driver failures may indicate hardware problems, insufficient power, or misconfigured BIOS settings. Check your system logs, DMESG, journal CTIL-XE, or /VAR log messages for relevant errors. If your workstation frequently runs out of memory, adjust your data loading pipelines to use more efficient formats like TF-Record, Parquet, or HDF5, or increase physical RAM where possible. Further efficiency can be gained by leveraging advanced frameworks for distributed computing and hardware acceleration. For multi-GPU setups, install NCCL, NVIDIA Collective Communications Library, to enable high-speed inter-GPU communication, crucial for data parallelism in PyTorch or TensorFlow. In distributed environments, software like Horovod or DeepSpeed can dramatically increase training speed and resource utilization. Automation accelerates both experimentation and deployment. Adopt Docker or Singularity containers for reproducible environments, especially when collaborating with teams or shifting workloads between workstations and cloud instances. Store environment and dependency details in YAML files for conda or requirements. Dext for pip to rapidly recreate or share your configurations. Consider using RAID for storage redundancy and speed, particularly RAID 0 striping for maximum throughput, or RAID 10 for a balance of speed and fault tolerance. Configure RAID during BIOS setup or within your OS using MDADM for Linux. For long-running tasks, configure your system's power settings to prevent sleep or hibernation interruptions. In Linux, systemd inhibit or custom scripts can ensure jobs aren't terminated or suspended unexpectedly. Where applicable, set up UPS battery backup systems and configure automatic recovery after unexpected power loss. Security and remote access are also part of optimal configuration. Enable OpenSSH for secure terminal access, configure firewall rules with UFW or firewalled, and disable unnecessary ports or services. For collaborative workflows, set up shared folders, user permission schemes, and version control access over SSH or HTTPS. Backup strategies are essential for research reproducibility and data protection. Schedule daily automated backups using rsync or Borg to external or networked storage. For cloud release, integrate with providers' CLI tools and set up versioned backups in S3, Azure, or Google Cloud buckets as appropriate. Customize your terminal prompt for actionable information, such as current Git branch or system usage. Tools like tmux or Screen allow you to multitask and manage sessions, especially during extensive training runs that benefit from local logging and recovery. For advanced users and larger data pipelines, integrate workflow and orchestration tools like Apache Airflow, Nextflow, or SnakeMake to automate end-to-end data processing and model lifecycle, from data preprocessing through training to deployment. Regularly audit and update your workstation's firmware, drivers, and critical software dependencies. Subscribe to vendor mailing lists, set up automatic update notifications, and periodically reboot after major updates to ensure kernel modules are correctly loaded.